flange, that's our BF. Then you have thickness of the flange, this is our TF. And then we have the web thickness, so this is our TF. Okay, so by looking at names, you are more or less familiar where's the part and where is the associate dimension. Okay, please get comfortable with this. Then we have second moment of area about the x-axis, second moment of the area of the y-axis. The next term I want you to look at is Rx, okay, and Ry. So R over here, you can see where R is defined as the radius of gyration. Okay. Now, what is radius of gyration? Okay. So the units over here is in millimeters. Okay. So how to compute radius of gyration? So we come back to here now. Okay. So I, the second moment of area, I, is equal to A multiplied by R squared. Okay. And as we already know, I is our second moment of area. A is our cross-sectional area. R is defined as the radius of gyration. So knowing that this is meter to power 4 meters squared, the radius of gyration is in meters. So if we were to calculate the radius of gyration R, right? So R is basically the square root of I over A. So if we pick two numbers, so I, for this case, we pick 346, so square root of 347 times 10 to the power 6, and then we divide by our area, which is 182, okay, 00. So when you calculate this, so 347 divided by 182, 00, square root the whole thing, you get 138.079 millimeter. So what we have, they round it off to 138 millimeters. So that is how they compute the radius of gyration. But how does this affect buckling? Okay, so now coming back to over here, we know that stress critical will be equal to pi squared EI over L squared A. Okay, so we are going to substitute, we're going to let R squared will be equal to what? So R squared will be equal to I over A. Okay, so R squared will be equal to I over A. So when that's the case, this term over here, so therefore, stress critical will be equal to pi squared E R squared over L squared. Okay. So we are now, I'm going to bring this, I'm going to put the pi squared multiplied by E, and then we will have over L over R squared. Okay. And the L, why we do it this way? Because from here, there's a term that we refer in buckling. Okay, the L over R is known as the slenderness ratio. Okay, and the L over R is known as the slenderness ratio. Okay, So now let's now look on how the L over R is helping us determine when buckling will occur. Okay, but before we go any further, there's something that I want you to put this in mind. Okay, to put this in mind. So to design a structure, to withstand or to design a structure based on buckling, or for this case, centric buckling analysis. Okay, so this is really important. Okay, this is when I put 3 star means it's important. So the first thing we do is we calculate PCR is equal to pi squared EI over L squared. Okay, critical load. So from here, right, usually we have a factor of safety which is equal to PCR divided by P allowable. Okay, so P allowable is equal to PCR over factor of safety. Okay, so now if we were if we were to calculate, so now we have a structure. And this structure has the load over here. So this is P. Okay. So we have to check, we have to ensure, that the P that we see over there is less than the P allowable. Okay, the P, okay, is less than P allowable. When this is the case, the structure will not buckle. Okay. However, this is still not enough. Okay. So we also have to, the next thing that so once this is the case, the structure will not buckle. Okay. The next thing we have to do is we have to calculate stress critical, which will be equal to P critical divided by our cross-sectional area. And we have to ensure that the critical load is less than the yield. You have to do this. This is to ensure the structure is safe. Okay. Now, what is so confusing about this? Okay. Over here, we calculate P allowable. Okay. And we have to ensure that the P, the applied P, or the P that you see over there, is less than P allowable. Okay. The next thing that a lot of times, this is just for buckling. Okay. The stress critical is we have to use the what? P critical value and not the P allowable. Are we clear? Okay, so this is very unique for buckling. Okay, and you don't want to mess this up. Okay, we don't want to like get this in the usually other analysis you use P allowable divided by area. Okay, this for buckling we use P critical. Okay, so the next thing that I want to highlight. Okay, this is important. Yeah, do not mess this up. I've been teaching this course. I think this is my probably 18th time, and always students make this very common mistake. Okay, now coming back to where we are, as I say, this is really important in Berkeley. Okay, so now we have to know when when is buckling analysis necessary. Okay, when is buckling analysis necessary? Okay, so the formula that we are going to use to see when buckling analysis is necessary is we are going to look at the critical load will be equal to pi squared E over LE over R squared. So now we see a new term. Okay, so LE is known as the equivalent length and is dependent on how the structure is held at both ends. Now this sounds familiar. The term over here sounds like, hey, how the ends are held at both ends. Okay. So yesterday we spent a lot of time on what? We spent a lot of time on boundary conditions, right? And deformation of the structure based on how it is held. So next, I want you to view this, okay? So I'm going to have this. No on. Computer not working, no. Human not working, not computer. Right. So what again, you have this diagram. So you can see from this diagram, right? The first one, right? When it's free, okay, when it's free, LE is equal to 2L, right? And then if both ends are pinned, LE is equal to L. Okay. And then when one end is pinned and the other one is fixed, LE is equal to 0.7 L. And then finally, if both ends are fixed, right, LE is equal to 0.5 L. So now, if we think about this, okay, so how this will affect our analysis? Okay, I repeat again, how this will affect our analysis. Okay, so the thing now we are going to do now is we are going to be considering, okay, we are going to put in numbers now. Okay, only by looking at numbers then we can visualize what is going on. Okay, so now for all situation, okay, we are going to deal for all situation now. So Okay, for all situations given where the stress allowable will be equal to 250 times 10 to the power 6 Pascal. Okay, and this is also equal to our stress critical. Okay, and then our Young's modulus is equal to 200 times 10 to the power 9 Pascal. Okay, and then the formula that we are going to apply. Okay, so for all cases, we are going to determine the L over R ratio. Okay, the L over R ratio. Okay, so now if we look at the L over R ratio, so I'm going to do the first one. I'm going to do the L over R ratio for L is equal to 1. Okay, so I'm going to draw lines coming down so you will not be confused which is for what. Okay. Okay, so we are going to calculate the L over R ratio. So we're going to do for both end pins. So the L over R ratio, not L over 2, come on, G. Now that or I'm going to put LE over R. Okay, LE. And for the first one, and this will be equal to square root pi squared E divided by stress critical. Okay, so this will be